Welcome back. Happy Friday. At the start of each class, we'll typically take a quick look at the calendar. You have this in the syllabus, but you don't need to take it out. This is just my way of showing you where we are and where we're headed. So today is class number 2. We're going to talk about average and instantaneous velocity. We handed out 2 projects last class, so hopefully we're going to keep up with that recommended schedule that's in the projects. And that'll put you on good pace to hand those projects in on time later this month. Any questions on the calendar? Okay, before we jump in with the new stuff, just a couple of resources I want to make sure that you are aware of. So if you log into Moodle, you'll find our course, and if you click on our course, it will look like this. And there's a few things in here you can mess around later on, but I just want to point to 2 things here. So one of them says class notes filled in, and there's a PDF right there. So if you click on that PDF, it opens up this thing. And so this thing is a full color reflection of everything that I wrote on the smartboard on Wednesday's class. And so when I'm writing stuff on the smartboard, you don't need to feel like you have to frantically copy everything that I put. This will always be available in full color, everything that I have on the smartboard. So really, it's better to make sure that you have enough brain power to like follow along with the class as opposed to just becoming like rote scribes in the class. Write down enough that you can recreate what happened, but know that this is a backup here available on Moodle. I don't post this every day. It's just a little bit of a pain to create this PDF every class. So I post it after class every Friday. So once a week it will get updated. But if it's a Monday or Wednesday and you are desperate for the PDF from that day, just send me an email. I will make one and email it to you. Okay? All right. Another resource. If you are in our Moodle page, there's something here that says link to playlist of lecture videos. So if you click on that link, it opens up this playlist. There's only one thing in here right now, but it will grow every class I record, and I post them here in this playlist. And I will play for you a few riveting moments from Wednesday's class. Here we go. It's like fastest growth rate, and then it's still growing, it's still increasing, and slowing down. That is just pure magic right there. So at the moment, this video has 3 views. I'm pretty sure all 3 of those are me just opening this thing up for you. But now that you know about it, it's going to blow up on YouTube. So, what do you do with this? Well, okay. So if you want to relive anything in class, if it would help you to see stuff a second time, it's there for you. If there's something that happens in class and you're too shy to ask a question, I hope you're not. I hope you just stop me and ask the question. But if you are too shy, maybe watching something a second time and rewinding it will be helpful. If you miss class, okay, well, there's no substitute for being here in class because then you miss out on all of the interactions in your groups, and you don't hear anything that you guys say when I ask questions and you answer. You're not going to hear any of that stuff. All you hear is me, but it's as close to substitute as I can come up with. All right, so that playlist will be there. I update it within 10 minutes of the end of class. The new video will be posted. Okay, any questions on any of those resources? All right. So next up, so here we are on page 12. So typically, all right, so we'll do our little daily summary, and then you're going to do some activity stuff. So in this class, we calculate instantaneous velocities and we connect them to tangent lines, 2 fundamental ideas in a Calculus 1 course. There's some stuff written here about the projects. I feel like I kind of said my piece about the projects on Wednesday, just that you want to keep up with them and do them a little bit at a time as opposed to waiting until the last minute. I think earlier today I heard one table making like a plan to meet together and start working on those projects together, and that is a great way to get these projects done. They are tough, but manageable as long as you work with other folks and make sure you take time and space it out and use your resources like me and people in Math Studio and peer tutoring. Okay, so that's about the projects. Okay, so typically we would do like the demo. That's me doing my thing first, and then the activities. That's you guys with your neighbors. We're doing things a little bit differently today. We're going to reverse that. Have you guys jump in here on the group activities. I will call you all back together at some point. I want to point out one typo. Actually, go past the page with the graphs to the next page. At the very bottom, I got to fix this. It says the word second. You guys see that word right there? That word second at the bottom of page 14. Cross that off on the bottom of page 14 and make it say first. Not second, but first. Okay, so with that change, you're going to come back here to page 13. You are going to write the names of your table mates again, either from memory or don't be shy, ask them if you have forgotten their names, and then you're going to jump in. There are questions on the next page about these 4 graphs. Raise a flag if you get stuck, and at some point soon I will call us back together. Okay, so like I said, we're going to do this little demo here together, and then you're just going to go right back to where you were with the zombie questions. Before we do, a couple of other logistical things. So again, almost every class has a homework assignment that will be due the very next class. In the beginning, I've got some latitude because I know we don't all have a book yet, but there is a textbook in the Math Studio and another one in the library. I always accept homework for full credit 1 class late. So even like for the homework that you're going to do over the weekend, if you don't quite have it done Monday, I'll take it Wednesday for full credit. But after that, I typically don't accept the homework for credit. I want you to do the homework no matter what, but this policy is my way of trying to encourage you to do the homework regularly as opposed to doing it all in one chunk, you know, like at the last minute. Yeah, Hunter. I'm going to walk around. I walked around a little bit before class and checked. I'll keep walking around and I'll check it today before we leave. Good question. Okay, here's an opportunity if there are any questions on the syllabus. I know there's a lot of information in that syllabus, but did anybody have any questions about the syllabus? Yeah. So if you read the syllabus, did you notice there are 2 options for grading? Yeah, so one of the options involves homework counting as part of your grade, and the other one involves homework not counting. And you're just going to pick one of those 2 choices. Later on in the semester, you don't need to commit one way or the other right now. The homework not counting isn't my way of saying, hey, don't bother doing the homework and it's not going to hurt. It's my way of saying, hey, there's oftentimes like 1 or 2 students who can get away with not doing the homework and still do okay on tests and quizzes and things like that. But by and large, doing homework is a very, very good way to make sure that you understand the concepts that we're going to be testing. So you're going to make that choice for me in like 4 weeks. You have plenty of time. In the meantime, before you've made that choice, I recommend everybody do all the homework as expected. And then at some point, if you decide it's not going to count, that's okay. Okay. All right. So let's jump in here on page 12 with our first demo. So this is a question about a ball dropping, and it appears to have nothing to do with the zombies, but they will connect to each other pretty soon. Suppose a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Let's estimate the instantaneous velocity of the ball at t equals 5 seconds. So we drop the ball, and we start the clock at that moment, and the ball is falling, falling, falling until it hits the ground. But it's going to take more than 5 seconds to hit the ground, and I want to know how fast is this ball going at t equals 5 seconds. So here is a formula, and if you're taking physics, perhaps you have seen this formula. It tells you the height of a falling object or an accelerating object as a function of time. So s is the letter we use for the height. It is 1/2 at squared plus v0 times t plus s0, and we just have to know what these different letters stand for. What is a? That's acceleration. In this case, it's gravity. T is time. That's how many seconds the thing has been falling. V sub 0, initial velocity. If you see a little subscript of 0, it almost certainly stands for initial, because that's when you start the stopwatch. It reads all zeros at the beginning of this experiment, the velocity at time 0. And S sub 0 stands for initial height. Again, it's an initial something, and S stands for height. Okay, so let's start plugging in to that crazy formula the facts from this problem. So S of t equals 1/2. Okay, acceleration is a constant here on Earth. Anybody happen to know that number? 9.8, right? So we're in meters here, so we're going to get the metric version of acceleration, 9.8. That's A equals 9.8 meters per second squared. If we were doing a problem in feet, it would be a different number. 32 is good enough for us. Okay, 1/2 at squared plus, okay, now I'm up to the v sub 0. What is the initial velocity for this ball the moment I let it go? 0. Before gravity takes hold of it, at that one instant in time, it is 0. So I'll put it, it's going to disappear in a second. But maybe in a different version of this problem, I throw the ball up at 10 meters per second, or I throw it down at 20 meters per second. So it's not always 0, but the word dropped says that it's 0 here. Plus, Last thing is S sub 0. Initial height of this ball at the moment we drop is at 450. Okay, so there's our formula. And we'll just crunch a little bit to make it look cleaner. So a half of 9.8, I guess that's 4.9 t squared plus 450. Okay, and we're interested in knowing what's going on with this ball at t equals 5 seconds. That's given in the problem. So how about we just plug 5 into this formula and see what that gives us. S of 5 is equal to, so we're just changing that 1t into a 5. 4.9 times 5 squared plus 450. So the idea here, whatever this calculation is, somebody with a calculator or phone help us out. But we drop the ball 5 seconds later, it's going to be at a certain height above the ground. Anybody have a number for us? Again? 572.5. How's that sound? 5 seconds after we drop this thing, it is 572.5 meters off the ground. Yeah, this awkward pause is my way of saying there's a problem here, right? Okay, so what mistake did, right, like this ball is supposed to be falling, and it's at 450 and then falling. How is it floating off into space here? It's that far from the ground. This is always a distance from the ground. Something should be negative. What should be negative? The acceleration, 9.8. If we put a positive 9.8, then we are saying positive 9.8 away from the center of the Earth, which is not how gravity works. That is a negative 9.8. Negative 4.9 on both. Okay, now we're good. The half is just always a half. You don't have to worry about putting a sign in front of that. But acceleration, if we're saying that, yeah, the 9.8 got smushed. Yeah, it went to 4.9. No problem. Okay, so somebody give me this number here. 327.5. Great. Okay, that's more reasonable, right? We drop it from 450, it falls for 5 seconds, now it's lower. Okay, that's better. Okay, what I'm interested in, so this is just like one snapshot, one moment in time. We took a photograph of this ball after 5 seconds and we've located it. It's 327.5 meters above the ground. But if you look at a picture of this ball falling, does that help you find the velocity? Like, can you find the velocity looking at a static picture? We can't. In order to get the velocity, we need like 2 pictures, right? I need to see a change. I need to see a change in distance, and I need to know how long that took. So how about, if we're interested in the velocity at 5 seconds, how about we answer a question that's easy? Instantaneous velocity is hard, but let's do an average velocity, and I'm going to put like some not standard notation. I'm going to say, let's take a look at the velocity between 5 seconds and 5.1 seconds. And average velocity is really easy to calculate. In fact, you did it with the zombies. We know that average velocity is change in what over change in what? Change in distance over change in time, and I can do some calculations here. So what I'm interested in is the height at 5.1 seconds. That's a number I don't know yet. And then I'm going to subtract the height at 5 seconds, and that's my change in distance, over my change in time. Well, 5.1 seconds minus 5 seconds, that's easy. 0.1 seconds is how much time elapsed in that little tiny time interval. Okay, so somebody with a calculator is going to help us out here. And plugging the 5.1 in is just a calculation. So if somebody has that number for us, that would be awesome. So we're doing the 5.1 squared times negative 4.9 plus the 450. One more? Yeah? 425.01. And then minus, we've already found S of 5, that's still this 327. And then divided by just 0.1 seconds. Okay, and if we could crunch that stuff and get us an answer. And while we're waiting on that answer, what would be a better time interval? This is good. There's not that much change from 5 seconds to 5.1 seconds, but I'd really love to hone in my attention on 5 seconds, that one moment in time. So maybe better than 5 to 5.1, 5 to 5.001, a little thousandth of a second in there. That's probably going to give me a very good estimate for the true instantaneous velocity at the one moment, t equals 5 seconds. Okay, so do we have a number for the 5 to 5.1, Aiden? How much? 975.1. What'd you get, Carrie? That sounds 322 point. $322.5. Yeah, I think Aaron's right? That's got to be more than 3. Oh, no, it's good. It's good. We like it. We like a negative answer here. Okay, so somebody's got a number we're going to crunch here. It's going to be negative something. And while we're waiting on that, we'll just fill in here. Again, it's supposed to be a change in distance over a change in time. So there's our formula. It looks almost identical to the one we just wrote in blue there. So it's s of 5.001 minus s of 5. That's our change in distance divided by the change in time. And all these calculations are going to look almost exactly the same. Top and bottom is the same. It's just the top has like s's. It's the functions on top subtracted divided by the inputs, the times on the bottom. Okay, so looking for two numbers here. Anybody have this first one? For Neri, 49.49. Okay, anybody have the green? So if somebody could get that green number for us, that would be awesome. In the meantime, we're going to take a look at a Sketchpad thing. So this is a piece of software called Geometer's Sketchpad. If you just do a Google search, there's like a free trial version that you can do. It'll time you out after, I don't know, 5 or 10 minutes of messing around, but you have enough time that you can play with stuff for free. If you like the software, you can pay for it. Okay, so right here, this purple thing is the height of our ball as it falls. It starts up here at the top at 450 meters, falling until looks like about 9 seconds and change when it hits the ground, okay? It looks like this is the path of the ball. It's not the path of the ball. The ball is not visible here. Time is happening on the horizontal axis. So this is just time passing on the right-hand side and the ball falling straight down. The ball is not going out, it's just going straight down. And you can see our fixed point right here. 5 seconds in, this ball is at a height of 327.5 meters. We saw that. And then I've got this varying point. And as I move this varying point, a lot of stuff is changing. So let's explain. The coordinates of the varying point are up here in green. And then I've got this line connecting my fixed point right here to my varying point. And the name of a line connecting 2 points on a curve is a secant line. You might have seen that phrase before, okay? And I've calculated the slope of the secant line here for some reason. We'll come back to that. So the first interval we did was from 5 seconds to 5.1. And so we're just going to go closer. I'm looking up here trying to get something close to 5.1 for that x coordinate. So I don't know, how about there? What was our average velocity from 5 to 5.1? Was it negative 49.49? Okay, and then we take a look right here, negative 49.50. I'm not exactly at 5.1, so we're off a tiny bit. But that slope of the secant line is somehow exactly the same as the average velocity that we calculated. Well, let's think about it. Slope is change in y over change in x, right? The y's in this case are the heights. The x's in this case are the times. When we did average velocity, we did change in distance over change in time. Wasn't that just change in y over change in x in this scenario? So we made an important connection here. The average velocity is the slope of the secant line, yes? So we made this connection between the algebra, the formula, and the graphical. The average velocity is the slope of that secant line. And then we wanted to go even closer. We keep that fixed point at 5, but we went to like 5 point, I don't know, 0001 or something. I don't think we ever got a number, but I'm just gonna start shoving here. I'll get as close as I can, maybe about there. I think that's about as good as I can do on this window. 5.0029 seconds. So I'm looking at a teeny tiny interval from 5 seconds to 5.0029. And the slope of the secant line, which is the average velocity on that little tiny interval, is negative 49.01. Do we have a guess as to, like, we had a negative 49.49, now we have a negative 49.01. I'm still not quite there, but I'm pretty darn close to a nice number. What's our guess for the true instantaneous velocity at 5 seconds? Maybe negative 49 exactly, right? Like, it's really close here. And in fact, I could also come from the other side, right? Like, just take a look at these blue velocities, and I'm just going to take this varying point and shove it closer and closer and closer, and we just make our best guess. Something around there, I think, is as good as I can do, and it sure looks like it's honing into maybe negative 49 from that side as well. And what I'd really love to happen is for that secant line to actually not hit 2 different points on my curve, but really just hit 1 point on my curve. Yeah, I'd really love for those 2 points to smush together and become just the same single point at 5 seconds. And we're going to have a name for that line too. Anybody know it? Tangent line. That's what that line is called. So the line that hits the curve twice is our secant line, and the line that hits the curve at just the 1 point is our tangent line. So I think I've got all that stuff written out. Let's just fill in some blanks here. Okay, number 3. Good definition. A secant line is a line that goes through how many points on a curve? 2 points. Go ahead and fill that in there. And now we're going to define tangent line poorly, but it's good enough for right now. Tangent line is a line that goes through 1 point on a curve. Okay, and now we connect to our average velocity here. The graphical interpretation of average velocity, it had to do with which line? Average velocity was which one? It's the secant line, and it's the slope of the secant line. That's what we're putting there. Slope of the secant line. And then 5, what is the graphical interpretation of instantaneous velocity? Slope of the tangent line. So if I put myself back in, like, taking the SAT mode, do they still have analogy problems on the verbal in the SAT? Okay, so then here's our analogy. Secant line is to average velocity as tangent line is to instantaneous velocity, okay? Average velocity and secant lines, those are pre-calculus concepts. Instantaneous velocity and tangent lines, that's the new stuff. That's a calculus thing. And we're going to be playing with tangent lines for almost the entirety of this semester. All right? So you are going to go back right now to wherever you left off in the zombies. And you are going to finish this page of questions with the zombies, including, like, you can just ignore number 8 here. Just go right past it, do number 9, go to the next page, do number 10. Just keep going with these questions until I call us back together with about 12 minutes left in class today. But the key here for you on number 7, which is that hard question that a bunch of us are thinking about now, is that if you want to know the instantaneous velocity, you draw yourself a tangent line and you estimate its slope, okay? And when you're drawing that tangent line, use a straight edge, maybe my green folder or something else. But draw a tangent line, estimate the slope, get some numbers, and we'll come back together in a little bit. So we're going to try to go through just the highlights of pages 15 and 16. There's some very dense symbolic calculations happening on these pages, and they're important. But for me, what I want to convey to you is, like, the big picture ideas that are going on here. And then you'll look at the details, like, over the weekend on your own. Here's the calculation. We're back to dropping the ball from the top of that tower. And instead of going from 5 to 5.1, or 5 to 5.001. We're going to be very general here, and we're going to go from 5 to, like, an arbitrary t. Okay, and the generality is going to cost us more in terms of how difficult the calculations are, but it's going to give us more at the end of the day. It's going to give us a lot of flexibility. So we know that average velocity is change in distance over change in time. And so instead of like s of 5.1 minus s of 5, I'll write that. That's what we had on the previous one. First calculation we did was this, right? And so instead of 5.1, it's now a general t. But the minus s of 5 is the same. And then on the bottom, it used to be 5.1 minus 5, but now it's a t minus 5, right? So it's just the same calculation, changing our specific 5.1 to a t. S of t, well, that was just a formula, right? I mean, we created this formula for any t, so you just copy it right there. And then S of 5, we did that calculation, that was easy. And then we just combine like terms, the 450 and the 327, and we come to this. And so this thing right here represents the average velocity on the interval 5 seconds to a generic t seconds, right there, okay? And what I'd really like to do, if I'm interested in getting the instantaneous velocity at t equals 5 seconds, at 5 seconds, I'd really like to send this number t closer and closer to 5, right? I want t to get really close to 5. Maybe t is 5.1, or maybe t is 5.001, or t is 4.99999, something really close to 5. And we've got notation that we're essentially introducing here. Maybe you've seen it in a pre-calculus class, but it's this thing right here. Limit as t approaches 5. The fraction there is the same fraction that we just ended with up above. And all we're doing is sending t to 5. Now, technically, what goes wrong if you just let t equal 5? Because that's what we'd like to do at the end of the day. You're dividing by 0, which is a problem. And in fact, if you plug t equals 5 in on the top, you will also get 0. And so we get this very strange creature, 0 divided by 0. It doesn't have any meaning to us here. But instead of like plopping 5 in, if we put in 5.001 or 4.999, we get some numbers that make sense, and we make our best guess, and we say, hey, it sure looks like all these numbers are approaching negative 49. That's what we think the instantaneous velocity is, negative 49 meters per second. Okay, different technique, but same idea, is instead of going from 5 to t, we could change gears just slightly and go from 5 to 5 plus h, where h is just going to be some little change in time. And ultimately, what would we like h to approach? If I want the 5 plus h to land almost right on top of the 5, I want h to be really close to 0. So maybe h is 0.1, and then it's just 5 to 5.1, which we've done, okay? So it's going to be the same idea. The calculations look a tiny bit different, but nearly identical. And so on the next page, I think here are the big calculations. S of 5 plus h minus s of 5 over 5 plus h minus 5. We do the calculations. You're going to do some number crunching with the help of a graphing calculator, or, you know, like Wolfram Alpha or something. And you'll, again, hopefully make your best guess. And it says, hey, looks like these numbers are approaching negative 49. And that's our estimate. Notice that in this case, we're taking h and sending it to 0. Before it was t going to 5, now it's h going to 0. That's going to be the one that we use almost exclusively, not the t going to 5. All right, so how can we put all this together on page 18? So you're welcome to, is this the right page? No, it's not. 17? There we go. So you're welcome to go to page 17 right now, but I'm going to go through this calculation faster than I expect you to be able to copy. And again, I don't want you to be mindless scribes. I want you to pay more attention than just like writing down everything I have. I'm going to make a PDF after class. You'll have this if you want it. So here we go. General definition. The instantaneous velocity of that function at a particular moment in time is given by this. That formula right there is important to us. I'm hoping it reminds you of s of 5 plus 0.1 minus s of 5 divided by 5 plus 0.1 minus 5. So the top and the bottom are things that look very familiar to us, and we're just generalizing. Instead of a specific 5, we're just going to call it a, but it's the same a in both of these spots. Instead of a specific 0.1, we're just going to call it h, and we're going to send h to 0 because we want that little interval to shrink as much as possible. And on the bottom, it's just h. Well, sure, because the 5 and the -5 are just going to cancel every time. So whatever we picked for h up here, it's going to be the same thing on the bottom when all is said and done. That fraction is important enough to give a name to. It's called the difference quotient. And when we talk about slope of a curve, we really mean slope of a tangent line of that curve. So we might omit the phrase tangent line, but we're really thinking slope of a curve now is really slope of a tangent line. And as we've seen, slope of a tangent line represents the instantaneous velocity. Okay, so now I'm going to try to blitz through this calculation. And we've got like 7 minutes. We'll see how it goes. So here's a problem from the reading. Suppose Ian throws a grapefruit straight up with an initial velocity of 100 feet per second from a height of 6 feet. Without a calculator, we're going to find the velocity of the grapefruit 1 second into its flight. Not average velocity, but instantaneous velocity. So here we go. We're going to use our same formula right there, the S of t formula, equals 1/2 of at squared plus initial velocity times t plus initial height. I'm just going to fill in the blanks with the numbers from this problem. Okay, acceleration. Is it negative 9.8 here? One subtle thing tells you it is not that. Upwards isn't the thing that bothers me. It's that this guy is going 100 feet per second from a height of 6 feet, not metric. So we're using the not metric acceleration. It's this negative 32. Notice the negative is in there. We got to have that. Okay, plus v sub 0. What's the initial velocity here? 100, and that is positive. This thing is going up. That's good. And then finally, S0 is the initial height, 6 feet. I throw it from like right around here. So plus 6. And we'll just crunch the numbers to make this a little cleaner. Negative 16t squared plus 100t plus 6. Okay, now we're going to calculate our fancy difference quotient. I'll write the definition, but I think it's right up above. S of, what is it? A plus H minus S of A, all divided by H. That is the difference quotient, and it's just the definition. It's supposed to represent slope of a secant line. Slope of a secant line here. Okay, how much is the A that we care about? That's the moment in time. 1 second, it is right here. 1 second into the flight. So those are my A's. S of 1 plus H. H is just staying. Minus S of 1. Same 1 in both. H is the same on the bottom. Okay, so now we're going to start plugging in. S of 1 plus H. This is the complicated part. That means change all of the T's to 1 plus H's. So this T and also this T, both becoming 1 plus H. So copying all that, negative 16, something squared plus 100, something plus 6. What are the somethings supposed to be in this case? 1 plus H. That's what goes inside. This is the most common place that folks make a mistake, is to say, oh, I know what S of 1 plus H is. It means plug 1 in for the T's and then tack on an H at the end. That ain't it. That's easier. I wish that were it, but that is never it. It is replace all the T's with what's in the parentheses. Okay, this is good. We still have this minus S of 1 business. Let's put that calculation, I'll put it up on the top here. S of 1 equals, so if I just plug 1 in for all of these things, negative 16 times 1 squared plus 100 times 1 plus 6, what is that? 106, is that 80, 90, 90? This is the interactive part of the class. 90? Thank you. Okay, that's S of 1. S of 1 is supposed to be subtracted here at the end, minus 90. Don't forget to divide the whole thing by H. Okay, big old mess. It's going to get a tiny bit worse before it gets better, but it's going to get a lot better if we can crunch through the algebra. I did that right, didn't I? 100, 6, yeah, I think we're good. Okay, so here we go. Equals, negative 16 is hanging out on the outside. 1 plus H squared. It is a FOIL. Imagine 2 of them in your mind, and we are foiling. 1 plus 2H plus H squared. Plus, I'll just go ahead and copy everything else there. 100 times 1 plus H plus 6 minus 90. I'll divide by H. Now we've got to get rid of these parentheses by doing what? distribute, lots of distributing. This is the one last step where it gets messier before it gets nicer. Negative 16 minus 32h minus 16h squared. 100 distributes, plus 100 plus 100h. Plus, and then we'll combine these two, I guess, right? That's a minus 94. All divided by h. Something is fishy. What do we do? 84. That's less fishy. So sometimes I make mistakes on purpose to see if you guys are paying attention. Yep, it's a learning moment right there. Okay, so that's good. And then something magical is going to happen. If you combine the constants, there's a negative 16, there's a plus 100, and there's a minus 84. What happens? You get 0. And when I made my intentional mistake a moment ago, I didn't get 0, which is why I said something was fishy. So you got to get 0. All those constants are going to disappear. Any polynomial we do this calculation for. Okay, so all those go away. That's lovely. And now we're going to combine the h terms. I got negative 32h there, 100h there, 68. Is that right? And then I think I only have one h squared, so I'll copy that. Minus 16h squared there. All divided by h. Super. A lot nicer looking now than it was a moment ago. What algebraic thing can I do on top? What comes out in front? Factor. H comes out of both, right? It turns out another number comes out of both. Like I guess 4 goes into both, but honestly, I don't even care about that. It's the h that's the key to this thing. So we're going to take the h out. 68 minus 16h, all divided by h. And then, what cancels? H cancels. And that is just wonderful because in front of the difference quotient, like at the top of this page, there's a limit as h goes to what? Limit as h goes to 0. And until this very moment right here, I wasn't allowed to put 0 in because that would be a division by 0. But now that there's no division anymore, I just have this, and I got no problems at all putting 0 in for h here. Technically, I'm not putting 0 in. I'm putting in like 0.01 or 0.0001. But we're all friends here. Let's just plug 0 in, right? Like that's what we're after. So then our final answer here, this is the instantaneous velocity. It's a limit as h approaches 0 of this thing we just wrote. And what do you get? 68 minus 16 times nothing. 68 feet per second. That is the velocity of this thing. Why is it positive? I thought this thing was falling. I threw it up. It still has not gotten to the top yet, right? That's a positive 68. It is still going away from Earth. If I wait another second or two, it's going to start falling, and that would be a negative number, okay? What's that? Superhuman? I think 100 feet per second is not unreasonable for somebody to, yeah, I think that's okay. Yeah. Yeah. Okay. All right, just on time. That was good. All right, so homework is in the syllabus. Have a wonderful weekend. Don't forget about the projects. A little bit of work on the projects every day. See you Monday.